Hi, this is Joe, and this is my project. I investigated whether or not trembling as a measure of postural sway can be linked to observed motion in the ankles. It's an exploratory project. So there are two primary views on postural sway in static stance. One is that it's primarily an error-driven process. So here, if we view the blue as some position which the central nervous system desires to be in, such as perfect verticality, any deviation from that blue point there is error. And so the primary task of the central nervous system is to reduce that error, or to reduce the size of the line between these two dots. Right? Now, the red represents center of pressure trajectory here, and it also represents center of pressure trajectory here. Yet we see another blue dot there. What we're seeing is a search-driven process, right? This blue dot represents rambling, which is a spline interpolation of zero force data points onto the center of pressure trajectory. So what we're really seeing here is a theoretical search by the central nervous system in the limits of stability. And that blue represents the search. The red around it represents actual center of pressure, some error in the system still present, but again, a search-driven process. Are these two views reconcilable? And that's what I investigated in the project. I used a data set from Dos Santos, Fukuchi, and Duarte et al. From Sao Paulo in Brazil, a data set with kinematic and ground reaction forces of human balance. All right, so in the study, they recruited a number of subjects, of which I only used young subjects for the analysis. They had subjects stand on a rigid and a soft surface at two different time points, obviously, eyes open and eyes closed. For both of those surfaces, they had stood on these surfaces for 60 seconds, 3 times, recorded kinematic and force plate data, which allows us to undergo angular acceleration calculation and rambling, trembling calculations. Let's first look at angular accelerations. So here we have a set of legs with some markers on them. This is the marker set used by the researchers. Our first goal is to define shank coordinates. We define a z-axis pointing to the right, from the middle of the ankle out to the lateral malleolus of the right leg, medial malleolus of the left leg. We then produce a quasi-y up towards the intermalleolar point, cross product those two to get the x-axis, and then cross the z and x to get the real y for the shank. This is the coordinate system used throughout my analysis. We do the same for the foot. Take that same z-axis that the shank used, produce a quasi-x pointing from the calcaneus towards the second metatarsal phalangeal joint. We then produce a real y from the cross of the z and quasi-x, remove the quasi-x, and then we get the x-axis. Real x-axis is the cross product of z and y. And this is going to be our real foot coordinate system that we used throughout the study, throughout my analysis. From there, we define 4 markers in the foot coordinate system shown below, calcaneus and the MTPs. And then we find the average position of these markers in static trial for about 300 frames, again, using rotation matrix from ground to foot to define it in the local system. We then define 4 markers in the shank coordinate system, the malleoli, the intermalleolar point, and the intercondylar point would be what I choose here. Find the average position of all 4 points, again, using rotation from the ground to the local frame. Then we use the least squares method as highlighted by John Chalice to infer the transformation from ground to local for foot and shank at each point in time in the dynamic trial. So then we can calculate R dot, which is the change in rotation matrices over a period of time by a numerical differentiation. We use that to calculate the omega tensor, which is a velocity, angular velocity tensor, by using R dot and R transposed. We can then calculate omega dot as numerical differentiation of omegas over a period of time. We then get alpha as a matrix from the subtraction of the omega dot foot from the omega dot shank, and then we multiply this matrix by the z vector, the z unit vector for any coordinate system, and we produce the angular velocity in that coordinate system, right? So we actually have the coordinate system for the ankle deduced here. On to rambling and trembling. How do we calculate this? What does this mean? Well, let's start with ground reaction force data, right? So here we have data from the ground reaction force in an anterior posterior direction, and we have the 0 force line clearly marked out for us here. What we're going to do is essentially imagine a little dot. At each point, the 0 force line crosses the actual ground reaction force data. We take those time points and we interpolate them onto the center of pressure data, right, which gives us a series of blue dots. You can see a few of them here, rather small, but you can see them. So we take those blue dots and we spline them together by a third order polynomial spline. And that is supposed to represent our rambling trajectory, which is the trajectory or the motion of a position defined by the central nervous system in time to help guide and direct postural sway. Again, searching for limits of stability. Trembling is simply the difference between rambling and the actual center of pressure. So any deviation as seen here, for example, center of pressure, rambling here, should be represented by a large trembling value. The larger the trembling value, the larger the restorative force towards the actual center of pressure trajectory that is seen on the screen. Okay. So what's the correlation between these two? Let's take a look. Here we have ankle angular accelerations and trembling plotted together. We have ankle angular accelerations as the peach colored lines here, trembling as the blue line. Again, these are in irreconcilable units. This is in millimeters. Ankle angular accelerations are in degrees per second squared. But again, plotting them on top of each other is a great way to visualize relationships. So here we have these as a relationship. And it seems like ankle angular accelerations don't change a whole lot. In fact, they hang around zero pretty much for the entire trial on a rigid surface. Whereas trembling seems to be a little more mobile. Again, can't compare units, but we see decreases and increases in trembling here that aren't necessarily reflected in any increase or decrease in ankle angular accelerations. So perhaps not strongly related on rigid surfaces. This may be different for foam surfaces. Again, same scale here from -15 to 10 degrees per second squared, same scale for trembling, -5 to 5. We see a pretty strong covariation in the trembling values and ankle angular acceleration values here. So again, peach color is ankle angular accelerations, blue is trembling. When one increases, the other increases. When one decreases, the other decreases. And this seems to happen at a zero time lag throughout the duration of the entire trial, which is interesting. This has never been explored. This is a novel finding. But what do the stats say? How strongly correlated are these actually? So I had two hypotheses. The first of which is that ankle angular accelerations would describe a large portion of variance with values of trembling in an anterior-posterior direction while standing on a rigid surface. I used a mixed linear model as shown below. Trembling is explained by or correlated with the right ankle angular accelerations, the left ankle angular accelerations, their interaction with random effects of subject and trial. This model actually produced a conditional R-squared of 0.01. Again, we're only explaining about 1% of the variation in trembling using the ankle angular acceleration data, which is very minimal, not much. Hard to say that the relationship is very strong at all if it's there, at least on rigid surfaces. There was a second hypothesis, and the hypothesis was that the direction of the correlation between ankle angular accelerations and trembling would reverse on a foam surface as a result of the force distributive properties of the compliant surface. And what we actually see in the data, at least, we see a pretty strong covariation here, but do we see a reversal of the effect of trembling on ankle angular accelerations? Or excuse me, do we see a reverse of the ankle angular accelerations on trembling? Well, not necessarily, because there wasn't much of an effect to begin with. But we notice from the statistics that the effect of the right ankle angular accelerations and left ankle angular accelerations did switch to positive when surface was added as a random effect in the mixed linear model, which suggests that yes, hypothesis 2 is likely true. However, it may not necessarily be all that relevant with the low explanatory power of the models in general. Conditional R-squared of 0.12 was shown for the second hypothesis, second statistical test. So what can we conclude from the above? Well, a couple things. First is that this is the first insight into connecting kinematics with control parameters and investigating rambling and trembling on foam surfaces. So certainly much more work to be done on this front. Trembling may have been the wrong construct to compare in rigid floor conditions. Rambling may have been a more intuitive connection. Again, rambling is going to be the active search process by the central nervous system. Trembling is the variation around that active search process. So perhaps in rigid surface conditions, there might be a stronger correlation between rambling and ankle angular accelerations, not necessarily trembling. However, the strong covariation seen in the data here deserves further explanation. Again, we're seeing this positive covariation here at a zero time lag. These things are happening simultaneously. So one process could be giving birth to another, or perhaps they're both the result of a different process, of a process upstream per se, that is resulting in their strong covariance in almost all the subjects across all data points. Really interesting to look at least in foam surface trials. Again, the retrospective nature of the study should cause some trepidation in the interpretation. As always, not as good as prospective, but still some value to the data here. Last thing, reconciling kinematics with control parameters could lead to new insights into clinical conditions, the diagnostics and interventions associated with them, and might help us in the clinical front, which is obviously a good thing. here are some of my sources. Thanks.